So this says this is section 3.3. In a different book, it was section 3.3. It's actually section 5.3 or 4.3. Who knows? It's not that one. So remember that if f prime is positive on an interval, then f is increasing on that interval. And if f prime is negative on an interval, then f is decreasing on that interval. Talked about that last week. We've actually sort of previewed this by doing related rates problems. So this leads us to the first derivative test for local extrema. Usually people just say the first derivative test. So if c is a critical number of a function f, which is continuous on an interval containing c, and differentiable on the interval except possibly at c, then there are two things that could go on that we're interested in. If f prime changes from negative to positive at x equals c, f has a relative minimum at c f of c. So that means, f prime changes from negative to positive, means that f changes from decreasing to increasing. In this unit, especially when you're doing your justifications, it's going to be super important that you never use the word it. Because we're talking about two different functions. We're talking about the function and its derivative. So a lot of times people will say things, ridiculous things like, if it is positive, it is increasing. And they're using it for two different things in that sentence. That one is immediately, all wrong, get out the red pen. Sometimes people will use it for one thing, and it's just not clear which thing they're talking about. Okay? And then if f prime changes from positive to negative at x equals c, f has a relative maximum at c f of c. So what we're going to do is we're going to look for critical numbers. That includes not only places where the derivative is 0, but also places where the derivative doesn't exist, but the function does exist. Okay? That's why it says f has to be continuous on an interval containing c. So we're going to look for places where the derivative is 0 or where the derivative doesn't exist. Those are going to be our critical values. And that's where we can have a local maximum or a local minimum. Only at those places. So, let's take a look at this one. The graph of the derivative, y equals f prime of x, of the function f of x, I never got around to finishing the sentence, is given. So this is the graph of f prime of x. Find the x-coordinate of each relative extrema of f of x. And this is going to happen a lot where we're interested in what's happening to f, but we're looking at the derivative. So don't be fooled by points like a. That's not a relative maximum or a relative minimum of f. It's a relative maximum of f prime, but not of f. B, on the other hand, is. So at x equals b, f has a, is it going to be a relative maximum or a relative minimum?
Maximum?
Yeah, it's going to be a maximum because the derivative changed from positive to negative. And we usually just abbreviate that rel max. What about at C? No, there's no sign change there. What about at D? Is this a critical point, first of all? Yes, because the derivative is 0. Do we have a relative minimum or a relative maximum at that point? No, there is no sign change. This is if you're thinking about this as being the velocity of a vehicle, it's negative, it's backing up, it stops, and then keeps backing up some more. So, nope, not there. Not at E. What about at F?
Yes.
What do we have? Yeah, f has a relative minimum because the derivative changed from negative to positive. And you have to get used to, these are kinds of questions that they ask you to justify a lot. You have to get used to saying that. All right? So let's find the intervals on which this cubic function is increasing and the intervals on which it's decreasing. So we'll start by finding critical points. To do that, we take the derivative. It's 3x squared minus 3x. I always tell students, first consider, is there a place where this function doesn't exist? Because people tend to go straight to finding the zeros of the derivative, and then they forget about looking for places where the derivative doesn't exist. But this is a polynomial. It exists for all x, so that's not a problem for us here. So we'll set this equal to 0. And with polynomials, we always factor. We find x is 0 and x is equal to 1 are our two critical points. Zero and 1. Now, for this particular problem, if you want to substitute in values, have at it. However, you guys are smarter than that. This is an upward-facing parabola. So I don't know exactly what it looks like, but I know it looks something like this, right? So I don't need to spend time substituting in values. I can go, okay, f prime positive, f prime negative, f prime positive. So f is increasing on open at negative infinity, closed at 0, and closed at 1, and open at infinity. And if you were asked to justify, I didn't ask it on this one, you would say because f prime is positive on, and that's open intervals, because it's not positive at 0. All right, so these would be open intervals. And then f is decreasing on the closed interval from 0 to 1. Because f prime is negative on the open interval from 0 to 1. All right. Let's do some other ones. Find the x-coordinate of each local extrema of the following functions. So we have f of x is 1/2 x minus cosine x. Again, we want this to be continuous on the interval that we're looking on, and it is. It's continuous everywhere. So 0 to 2 pi, not a problem. So I take the derivative, f prime of x. That's going to be 1/2 plus sine of x equals 0. This is one I can solve by hand because it's not a polynomial, it's just a constant. So this is sine of x is equal to negative 1/2. So I usually think of where is sine equal to positive 1/2 first, so I don't bend my brain too much worrying about different quadrants and stuff. So where is sine equal to 1/2?
30 degrees.
So we don't do anything in degrees in this class.
Pi 6.
Pi over 6, exactly. But that would be in the first quadrant. So it's got to be some multiple of pi over 6. Well, let's see. Which quadrants do we want to be in if we're going from 0 to 2 pi? Where sine is negative.
Fourth quadrant.
Fourth quadrant, and also,
Second quadrant.
nope. Did you guys ever use the little acronym, all students take calculus?
Yes.
So sine is positive in the first and second quadrant, so it's negative in the third and fourth.
Yeah.
So this is going to be 7 pi over 6. Or, over here, not quite 2 pi, x equals 11 pi over 6. So we're only actually looking, I put arrows on the end, but we're really only looking between 0 and 2 pi, right? And 7 pi over 6 will be somewhere around here. And 11 pi over 6 will be about here. And again, you could use test points for this. However, I know that sine is positive in the first quadrant, right? So I know f prime is going to be positive all throughout this region. And because we've just taken the sine graph and shifted it up 1/2, what's happening is it's positive, then f prime is going to be negative here, and f prime positive here. So f has a, what happens to the graph of f at 7 pi over 6? F prime is going from positive to negative.
Relative minimum.
No. If f prime is positive, remember the function is increasing, and then it changes to decreasing, so f has a relative maximum at x equals 7 pi over 6. And they didn't ask me to justify it, but it's a short justification. I'm going to add it on here because f prime changes from positive to negative at x equals 7 pi over 6. And then what happens at 11 pi over 6?
Was a relative minimum.
Yeah. F has a relative minimum at x is equal to 11 pi over 6 because f prime changes from negative to positive at x equals 11 pi over 6. All right, let's move on to this one. This is a function where I'm like, I don't know what that function looks like. But I'll take the derivative, f prime of x is 2/3 times x squared minus 9 raised to the negative 1/3 power times, because we all believe in the chain rule, 2x. So this is 4x over 3 square roots of x squared, cube roots of x squared minus 9. Again, I always look for places where f prime doesn't exist. And there are places on this one. Where does f prime not exist?
3.
And? And negative 3. And where is f prime equal to 0? This is not a trick question.
0.
At 0. Right? We got to make the numerator 0. So those are my 3 critical points. And unlike some of the previous ones, I don't have a clue what this thing looks like. So I'm actually going to substitute in values. And again, you don't have to compute the exact value of the derivative. You just need to know whether it's positive or negative. So if I pick, for example, negative 4, substitute that in, the numerator is now negative. Negative 4 squared is 16 minus 9. That's going to be positive. The cube root is positive. The 3 is always positive. So I know here that f prime is less than 0. If I substitute in, say, negative 1, my numerator is still negative. My denominator, negative 1 squared, is 1, minus 1 is negative 8. I'm taking the cube root of negative 8, which I can do. It's not the square root, so we're okay with that. That's negative. I have a negative numerator and a negative denominator. F prime is positive. If I substitute in positive 1, it reverses. The numerator is now positive. The numerator is still negative, though. So f prime less than 0 and greater than 3, numerator positive, denominator positive. Now this alternating behavior doesn't always happen. Students get lulled into that because there's way more functions where it does happen this way than it doesn't. But don't make the mistake of, oh, these always alternate. Right? People think that that's the pattern. A lot of times it does. If it's a polynomial, it usually does, but not always. Like if you have a double root, it doesn't. So we're just telling about relative minimums and relative maximums. So what happens at x equals negative 3?
Is it relative minimum?
Yes. At x equals negative 3. Do we have another one where we have a relative minimum?
3.
Yeah. Might as well get them both in. F has a relative minimum. And at x equals 0?
Is it relative maximum?
Yeah. And in the interest of time, again, I'm not going to justify those. They didn't ask me to. But I did want to get to this one. I like giving this one at this point in the year because when students start taking the derivative, they immediately jump in and start using the quotient rule. Not the best idea. Because the original function is x plus x to the negative 3, because it's 1 over x cubed. So the derivative, f prime of x, is just 1 minus 3x to the negative 4. So that's 1 minus 3 over x to the fourth. I do like to have a common denominator for this. I find that it makes things easier. So this is going to be x to the fourth minus 3 over x to the fourth. So where does f prime not exist? At x equals 0. And f prime of x is equal to 0, well, that means that x to the fourth minus 3 has got to be 0. So x to the fourth is 3. So x is equal to plus or minus the fourth root of 3. Icky. All right, so we'll use a number line to kind of help us. Let's see, our critical points are at 0, the fourth root of 3, and the negative fourth root of 3. All right, so when you're picking values to check, especially on one like this, people are like, oh, I don't know how big the fourth root of 3 is. Well, okay. Then do something silly. Go, okay, I'm going to make x negative 100. Raise that to the fourth power. It's clearly positive. Minus 3, still positive. Denominator positive. F prime positive. Here, you're like, I got to pick something between those two. Okay. So negative fourth root of 3. Like, okay. Square root of 3 is like 0.7 something. And then the fourth root, so I mean, it's going to be something kind of smallish. Let's see what it is. Gotta wake my calculator back up. 3 raised to the 0.25 power. 1.316. Okay. So I could pick negative 1. They're not going to be crazy about things. So if you just think about it, the fourth root of 1 would be in between these two, and the fourth root of 1 is 1. Or sorry, the negative fourth root of 1. So if I pick negative 1, the numerator is now negative, the denominator is positive, f prime less than 0. If I pick a positive 1, my numerator is still negative, my denominator still positive, and you get something that I said was going to happen. We don't have a change here. So here, if we pick a really big number, we get f prime positive again. And it shouldn't be surprising that this is an even function, because all the powers in this, including the one on the 3, it's x to the 0 power, are all even. So this is an even function. The left side and the right side should look exactly alike. So f has a what at x equals 0? I mean, at x equals negative fourth root of 3. All right, so you know this part. F prime's positive, so what is the f doing? If f prime's positive, f is increasing. And then it's decreasing. So we have a local maximum at x equals negative 4th root of 3. And f has a local minimum at x equals positive 4th root of 3. By the way, if they asked you for the intervals on which f is increasing or f is decreasing, there's only 3 intervals. On this whole interval, f is decreasing. You're like, well, at this point, isn't the derivative 0? Yes, but remember, increasing and decreasing is always on an interval. So just because the derivative is 0 at that one point doesn't matter. If you think about cubic functions, all right, the derivative is 0 right here, but this function's increasing all the time. Right? It flattens out momentarily. All right, any questions about any of that? Okay.